So let's just get to it. As I said before, we are in these several programming courses in Yamagata University where we aim at eventually getting to computer vision and deep learning, but where we started from very basic programming concepts, variables, ifs, and so on and so forth. And in this series of videos, we have been making our way through algorithms and data structures and are currently in the end part of this course and speaking about complexity of algorithms. In Unit 7, we will speak about recursive programming and also introduce as many complexity classes as we possibly can. As I did last time, and to avoid possible connection problems, here I just opened the Jupyter Notebook here. I have downloaded file, download, and then download Jupyter Notebook, the file, so I will be running it in my computer. Okay. And let's just start. The first thing that we have to do is actually define what recursive programming is. And I'm going to do that by first just saying that a recursive function is a function that calls itself. That, as we will see during this session, is a very important part of it. But something that's sometimes not mentioned when defining recursive programming is that recursive programming is based on mathematical induction, on the principle of mathematical induction. And I want to speak about it for a second now, because I think it will help us understand how recursive programming works and how to code recursive algorithms. In particular, you may remember the principle of mathematical induction from your high school classes or from your calculus or algebra class in university. Basically, this principle, which is also sometimes referred to as the domino principle, because it conjures these images of the dominoes where you just make sure of two things. First, you set up a line of dominoes and make sure that every piece tumbles the next one in sequence. And the second thing that you make sure of is to just give the first domino in the sequence a good push. And then with that, you can be reasonably sure that all the dominoes are going to fall. The principle of mathematical induction works in an analogous way. You have a mathematical property that you want to prove, and I'm going to be proving one now. So we have our first mathematical proof, and don't worry because it's going to be pretty short. It's only going to take, I think, 3 slides. We have a mathematical property that we want to prove, and that works over the natural numbers. So from 1, 2, 3, 4, and so on and so forth. And we want to prove that the property is true for all the natural numbers. And we will do something that's a bit analogous to that domino image that I was saying. We will make sure that the property holds for what we will call a base case, small initial case, and then we will prove that if I believe that the property is true for a certain position, which I will call n-1, then the property also has to hold necessarily for n, for the next number in sequence. If I can prove the two things, there is somewhere where I can start. The property holds for, let's say, 1. And then I can prove that if the property holds for n-1, then it also holds for n. Then automatically, by the principle of induction, I can claim that the property holds for all natural numbers. You can think of it as, well, I saw that it holds for 1, and because it holds for 1, and I saw that when it holds for one number, it also holds for the next number, then it also holds for 2. And if it holds for 2, then it also holds for 3, and so on and so forth, and it holds for all of the natural numbers. That's the way proofs by induction work, and this looks like a pretty intuitive principle to consider. Pretty important in mathematical reasoning too. And to see it illustrated, to see an example, let's consider this property. The sum of the first n numbers. We will code this recursively in a little moment, but let's start with a mathematical property. So if I add up all the numbers 1, 2, 3, 1 plus 2 plus 3 plus 4 up to n, up to some point, then my result is n times n plus 1, everything divided by 2. This is a property that seems to have been known for a long time, since the time of the Greeks, but which nice story says that was discovered by the great mathematician Gauss in primary school. Apparently Gauss as a child had been misbehaving in school. I suspect he might have been bored in primary school mathematics, being a total genius as he was, and his teacher made him add up the numbers from 1 to 100. He immediately answered 5,050, to which the teacher, quite shocked, replied, okay, now do it to 1,000. And when Gauss also replied immediately and correctly, the teacher was very surprised. Gauss had essentially discovered this formula in his head, which is something that mathematical geniuses tend to do. He had not proven it by induction in his head. He had realized that if you had to add all the numbers from 1 to, say, 100, when you do 1 plus 100, you get 101, and when you do 2 plus 99, you get the same thing, and when you do 3 plus 98, you also get the same thing, 101, and so on and so forth. So he realized that what you're getting is always the same addition, but you get it, so you always get n plus 1, but you get it n divided by 2 times. Okay, so n plus 1 is 101 when n is 100, and I do couples of numbers, so I get this. So this is a simple way to see that the property is true, but let's actually prove it by induction. So I want to prove this property, and let's first do a base case. So I need to prove that the property is true for a number where I will start to see that my property is true for the base case. I can actually choose whatever base case I like, and that will mean that my property will hold from that number forward. So I could prove this for n equals 7. But as you will see, I can just choose n equals 1, and I can see easily that it does hold. So when n equals 1, the property becomes 1 equals 1 times 2 divided by 2, which is true. Yay! So I have proved my base case for this mathematical property. The property holds when n equals 1. Second thing that I need to prove is the general case. If the property is true for n minus 1, then it is also true for n. Can I prove this? N minus 1 holds, then it means that necessarily n also holds. Yep, let's do some algebraic manipulations. I want to see whether or not this equals this other thing. But 1 plus 2 plus up to n is the same thing up to n minus 1 plus n. And this thing, by induction, I already know that holds the property. So this thing, 1 up to n minus 1, 1 added to 2 to 3 up to n minus 1 is the same thing as n minus 1. So I'm substituting n minus 1 in this property. N minus 1 times n minus 1 plus 1 divided by 2. As n minus 1 is n, this thing is n minus 1 times n divided per 2. Okay, so I now substitute this thing into this equation, and what I get is that the sum of the first n numbers is this thing that I got here, which was the sum up to n minus 1 plus n. And then I just take n as the common factor and get this thing, which I can then, sorry, there is a bar missing here. This should be divided by 2, which is n times n plus 1 divided by 2, okay, which is what I was trying to prove. So I have checked that the property holds for 1, and then I have checked that if it holds for n minus 1, it must also hold for n. So I have proved that the property holds for all integer numbers. So let's get back to the programming. After all, that's what you guys came here for. What is recursive programming? A recursive function, as I said before, is a function that calls itself. But as we will see, that results in a type of structure that's closely related to the mathematical principle of induction that we have seen. Basically, we will have a function that will call itself. This function will have some parameters, and we will need the parameters to decrease in some sense. We will be seeing it with more detail in all the examples in this session. Function calls itself, the parameters decrease. This decrease of parameters is closely related to the base case in the induction principle. So, sorry, not the base case, the recursive case in the induction principle. So there is a recursive call, the function calls itself, and the parameters of the function decrease. But then you also need to have a base case. You need to have somewhere to stop the recursive calls. Once you reach that, then you trace back all the tree of calls to the start, and then you can get the answer to the question that you started with. We will see this, which at this point is very abstract, very slowly and very detailedly, but you can picture this with this very nice example that I lifted from this Stack Overflow thread that you can check. In order to picture this structure of calls that go deeper and deeper and deeper until they reach a base case and then go back, the author of that post proposes, let's say, nursery type rhyme. A child couldn't sleep, so her mother told her a story about a little frog who couldn't sleep, so the frog's mother told her a story about a little bear who couldn't sleep, so the bear's mother told her a story about a little weasel who fell asleep. Up to here, we have had the same structure. Couldn't sleep, so the mother told, okay, so we have something that's happening again and again and again. The same function, the same thing is being called again and again and again, until we reach a point where things stop, the base case. This would be the recursive calls, and this would be the base case. Okay, and once we are at the base case, so the little weasel has fallen asleep, then we go back, and the little bear fell asleep, and the little frog fell asleep, and the little child fell asleep. This is a structure where we go deep, 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 deep into a series of recursive calls, then reach the base case, and then go back and use the result of the base case to construct the answer, the correct answer for the recursive calls, is going to be our go-to structure for the recursive functions that we will be making.